Uh, so mostly in this week, the assignment is on actually BCS theory. Although the Ginsberg-Lambda theory and its thermodynamics was introduced, but there is no question from that part actually. So that will be in the next week's assignment. So the derivation of BCS theory is pretty big actually. Okay. In the first lecture also it was not solved fully. The line by line solution was not there. I think I am also not going to going to solve each line actually. So what I'll planning to do is that I am preparing a detailed note on the solution of the BCS theory. So just the energy derivation and energy gap equation basically. I'll share once it is done, maybe day after tomorrow. Okay. And it will be on the same folder where I mean these notes will be uploaded. Okay. So the first question that we have for this assignment is that explain flux quantization in a multiply connected superconductor. Okay. Okay. So the general flux quantization relation that we have is, so suppose we have a superconducting material, and then we are seeing somewhere here, let's say. So this is simply connected. I will explain what is simply connected and what is multiply connected. So the equation is, oh, sorry, this is surface integral, where phi 0 is flux quantum. So here H by E is usually known as flux quantum. Okay, but for superconductivity it is 2e because we have a Cooper pair which consists of two electrons, right? So that's why it is 2e. This is of the order of 10 to the power minus 15 Tesla into meter square, I think. Yeah. And so Js is the superconducting current. So let's say we have a big bulk superconducting materials. Let me draw. So we have a superconducting material, and then we have some loop, okay, within the superconductor we consider. So this is, let's say, C, closed loop, of course, and so Js is the current, supercurrent density, and this elemental length is dl. So we have lambda Js dot dl, and then if we apply magnetic field also, then so suppose the magnetic field is also there, so then the S is representing the whole surface, okay, closed by the or created by the closed loop. So P dot ds equal to n phi, and n is an integer. So this is the case for simply connected, meaning you take a loop. So the whole material is superconducting. So we have a, let's say, one loop C1, and then another loop somewhere there can be C2. All are superconducting because the whole bulk is superconducting. Okay. So, so this kind of loop in a material where there is no normal region in the material. Okay. So all over the material there is superconductivity once we go below TC. Okay. So this is called simply connected because so these are the loops. If you shrink the loops, you are able to. So if you allow this loop to shrink, then you can reach a point where the loop is essentially will be a point, and then there will be no flux enclosed by this loop, right? So this is allowed for a simply connected superconductor. Now, what happens for a multiply connected superconductor is that, so suppose you have a bulk superconducting material, and then somewhere here, so let me draw it. So this is the normal region, okay? So this is normal, and this is superconducting region. Now you draw a closed loop in the superconducting material, something like this, okay? And this is called multiply connected. The reason is, the name is kind of confusing, but multiply connected we call it because we have a superconducting loop or a loop within a superconductor actually, and then within the loop encloses a normal region. So here there is no superconductivity. Okay, you can think of that you have a ring-shaped superconducting material, and so as long as you are within the ring of the material, you are having superconductivity. So that material is showing superconductivity. Once you are not within the ring, uh, so basically it's uh, air, let's say. So right. So then it's multiply connected because there are multiple region. One region is superconductor. So this whole region is superconductor. So this whole region is superconductor, and then this particular region is normal, right? So there are multiple phase coexist. So that's why we call it multiply connected. Now the difference for the relation between the flux quantization expression. So this is let's say flux quantization expression. Now for a simply connected material, it can go to zero. So flux quantization can go to zero. And this flux quantization is essentially means enclosed by the closed loop within superconductor. Okay, go to zero. If we shrink the loop to zero, basically, if we shrink the loop to have only point, okay. So, and this is allowed in simply connected superconductor, whereas for multiply connected, this condition is actually not allowed. So you can only shrink this particular loop up to this point, okay. So enclosing the normal material, you are not allowed to, go below that actually. So that means a finite amount of flux will always be, enclosed within the loop, right? So again, here you will have a magnetic field passing, applied within the material. Uh, but so yeah, so then what will happen is that flux quantization. So this was for simply connected. Uh, yeah. So the flux quantization holds when the conduct, sorry, contour. So contour means this loop. Swing to the contour, uh, just outlining this normal region within the superconductor. Okay. So because this contour can only be shrink up to a point, so that means there will be always some flux quantization enclosed by this in multiply connected uh, superconductor. Okay. So yeah, so that is the point. So you will always have some B dot ds to be there. Okay. So it will be n or n prime depending on how much is the I mean the surface and so on. And also you will have some. So we'll have some JDS, right? JS dot DL. So even if you go to up, you can only allowed to go to up to this limit actually. Okay. So that means this there is n prime can always be some non-zero. Okay. So that's the difference between a simply connected and a multiply connected superconductor. Okay. So any confusion? Okay. So let me go to the next problem. So next problem is actually full derivation of BCS Hamilton, I mean BCS energy and gap equation. Okay. Just let,
Hello.
yeah.
Can you repeat the argument? Just, I mean, the difference between the simply and multiply
Yeah.
connected and
Yeah.
how it connected it becomes non. Can you?
Sure. So okay. So simply connected means I mean okay. So suppose you have a I mean superconducting region, and then there are multiple contours that you are considering. Okay. And this multiple connected sorry this each contour this quantization condition that we have written here. So this is the flux quantization condition. Why? Because I mean you are taking the line integral of supercurrent density, and then if we have some magnetic field applied in the material, then also the magnetic flux that is enclosed by this C closed loop. So that flux is going to have some integer number, okay, in of course in units of phi 0. So that's what the flux quantization equation is. Now for a simply connected region, so this means these are the simply connected regions, and there is no hole in the superconducting region. Okay, so the whole region, so this whole region is superconductor. Okay, here the flux quantization holds for each and every contour. So C1 and C2, and then there might be other region. So all these region have their individual flux quantization relation to be valid. Okay, so that is simply connected. Now imagine we have a superconductor where so this part is filled with air. Okay, let's say air. So this is definitely not superconducting region, whereas all these other regions, so this particular regions are superconducting. Okay. Now now here what will happen is that flux quantization holds when so okay so this flux quantization relation holds only when uh, you basically shrink up to this point actually. So you actually cover the boundary of the non-superconducting region, let's say. Okay. And this has other implications actually. So there is something called topological charge and so on in the superconductor. So here you have this well defined you will have some well defined topology, I mean the flux that will be enclosed because of this, depending on this particular uh, loop in the superconductor actually. Okay, so let me write down, that will be easier. So the case 1, let's say, so this case A and case B. So for holds for each contour. Okay, and this you can shrink. So this contour shrink to uh, even a point. What this means is that whenever you hit a point, so you have a region something like this, and you are I mean decreasing the this loop area or the loop size, then you somewhere at that point you will hit a point. So basically that means there will not be any flux, and that particular case will correspond to n equal to 0. No flux is enclosed by this point, let's say. Okay, so you are allowed to do that in simply connected region. Now for case B, so we have, let's say, so this is the normal region. Again, I am writing here, but it is essentially representing normal region. Okay. Uh, so this, so you have a loop something like this, and you are syncing this. You are only allowed up to this point. Okay. So up to this point, you are allowed to sync this particular loop. So after that, you cannot sync. So that the flux quantization is valid only up till this point. So this actually depends on the C, right? So here, so in this case, the C loop can be kind of arbitrary, right? You start from the covering the whole region of the superconductivity, and you come to a point. In the whole region, this flux quantization condition is valid. But in the multiply connected region, multiply connected because there are multiple states. So this is, I mean, normal state. This is superconducting state, and in here you cannot go in the, I mean continuously from a loop to a point. In fact, you cannot hit a point. So you just, the flux quantization is valid up to this point. Okay, that's the difference. Is it clear?
So actually, I have a small confusion. I mean,
Sorry,
more,
your
most
voice
of
is
the
not clear. Yeah, please be a
hello.
little louder. Yeah.
I mean, am I audible
Yes, yes,
now?
now.
Uh, Actually, thanks for more clarification. It's more clear. I mean, but I have a little confusion left. That
Mm-hmm.
suppose in the multiply connected case you are considering,
Mm-hmm.
if I consider the loop not surrounding the air, if I
Mm.
consider, is it possible? If I
Yeah.
consider the loop
Mm.
only inside the ring, only inside the ring, then that could be synced to a point, right? That could be synced to a point because if I consider the ring inside the ring,
Mm-hmm.
uh, uh, but if I enclose the air, then your argument is correct that I am not able to shrink it to a point because I will be stuck on the boundary of the air.
Mm-hmm.
So, I don't know. I mean, whether my question is valid or not, but maybe, yeah. So
No,
I am
actually,
confused.
yeah. So, yeah, no, it's clear now. Actually, so maybe my words also have not been clear. Okay, so let me re-explain things. So, so you have a, I mean, multiply connected superconductor. Okay, now you enclose somewhere here. Okay, or somewhere here. So there is no guarantee that the flux will be quantized. I mean, this expression is valid, but then the problem is you may not. So this particular thing you derive or you, I mean, measure whatever it is, then you will not, you may not get that n prime to be integer for a multiply connected. Okay, so you take some arbitrary, I mean, uh, loop within the superconductor. So n may not be, so rather it is better to call this quantity. So lambda closed loop integral of C j dot dl plus surface b dot ds. So this quantity can be non-zero. That's not a problem. But this may not be integer number, okay, for a multiply connected. Just because you have a air filled state, normal state within the superconductor itself. Now, when can it be quantized? You just only when hit this particular region. So let's call it C1, C2, and this is, let's say, C3. So this for C1 and C3, so they are not integer, not guaranteed to be integer actually. Okay, and so this particular quantity for C2, let's say, when it exactly, uh, I mean, encircles the normal region, then it is it is again integer. So n belongs to I. So is this clear now?
Yeah, I got it right now. Now, actually, it has to be I mean, the contour to be traced on the throughout the boundary between the normal and superconducting state.
Right,
In that case,
right.
only we will get the flux quantization,
Yeah,
right?
yeah. In earlier case, yeah, that's true. Actually, that's the case. In earlier case, any region you take, depending on its area, depending on its the loop size, you are having flux quantization, and of course, with different quantization number, right? N will be different for different size of loop. But here, you are kind of having a fixed integer and fixed flux quantization condition, depending on the uh, your normal region's area or loop size, whatever you call it. So this is kind of fixed, determined by the how you make the material, or yeah. But for a simply connected, you create a loop and then you make it bigger. There will be another flux quantization number and so on. Yeah. So any questions? Hello.
It's fine from my side.
Okay. Okay. So the next question is so next question has a three part. So write down the BCS Hamiltonian and then compute the expectation values of kinetic energy and potential energy for problem 2. I mean, the above part, BCS Hamiltonian, in terms of coherence factors UK and VK. The third question is convert the energy obtained in the previous part in terms of single particle variable, which we usually I mean, take theta as a variable, such that the coherent factors are sin theta k cos theta k, and then minimize the energy to obtain the BCS gap equation. So this, the whole problem was actually solved in the lecture 1 for week 2, but I will upload a detailed solution, as much uh, extra line I can put actually. Okay, yeah. So I'm skipping this part, and then question 3 is exactly the same actually. So let me write the question 3. So this is for all k and k prime as long as their energy. So all k and k prime such that h bar actually the energy corresponding to this k and k prime. So energy k and energy at k prime uh, lies within, let's say, h bar omega d. And of course, the h bar omega d, the energy scale is always measured from the epsilon f. So we have a Fermi surface, which is at epsilon f Fermi energy, and then there is a small region h bar omega d surrounding this point, surrounding this sphere. Okay, and this needs to be done by solving two particle Schrodinger equation. Okay, and then there are other details for a singlet state wave function. Singlet state means you will consider one is up electron and another one is down electron. So that so this will be the spin part, and then the real space wave function part will be symmetric. Okay, so that the total wave function of two electron, or for that matter any fermion, is always antisymmetric. So that so the spins are in singlet state, and then the real space part of the wave function are symmetric. And then the typical assumption that electronic density of state is predominantly from the contribution at the Fermi surface from this region. Okay. This is actually essentially kind of the same question as question number two. It just says that two particle Schrodinger equation and so on. But you can actually, so there is a solution in the real space formalism as well. Okay, so the only difference we can have is that we can either solve it exactly like question two. So there also we had a BCS Hamiltonian something like sum over k and then sigma. Sigma denotes the spin, some energy, or I'm writing epsilon actually. So epsilon of k sigma, c k sigma dagger, c k sigma plus again k sigma, and then there will be another index L here, VKL, CK up, dagger, CK, sorry, minus K down, dagger, and C of minus L down, C of minus, sorry, L up. Okay, okay. So let me, so this was the kind of, the momentum space, although it has a four component of, I mean, two particle interaction, VKL. So the similar thing will be there. Okay. This is a lengthy solution actually. So let me go to the other parts, 4, 5, 6, and 7. No, sorry, 6, and then come back to this. Okay. So that solving this equation doesn't eat up other problems time fully. Yeah. Okay. So the question 4 is, considering pairing of electrons mediated by phonons, draw Feynman diagrams of two processes in which an electron with momentum plus k releases a phonon with momentum q, which is lit. So let me write down actually. Okay, so this is the question. Uh, so it says draw Feynman diagram of two process in which an electron with momentum plus k releases a phonon with momentum q, which is later reabsorbed by another electron with momentum minus k. Okay, so this is the first part of the question, and then there is another part. So suppose we have an electron with momentum k, and then it releases a phonon. So let's say this is q, uh, which is later absorbed by another electron with momentum minus k. So we have, let's say, another electron with momentum minus k, and then it absorbs, so minus k plus q, and then so this particular electron released the momentum, so k minus q. Okay, so the total momentum is gone down. Okay, so this is for case 1, let's say, and then for case 2, and in the later, the electron with minus k releases a phonon, so minus k releases a phonon which is later absorbed by electron with plus k, so plus k, so plus k plus q, and then this will be minus k minus q. So these are the two process, Feynman diagram process. Okay, so the curly line means they are phonon, they represents phonon, and then the straight lines represents the electrons. Okay, so this was the 4A part actually, and then B part will be clearly identify the initial, intermediate, and final state energies, and show that this process. Okay,
Hello.
so yeah, sure.
Sorry to interrupt
No,
you.
no,
Actually,
yeah.
so this Python diagram things actually we studied long back in our MSc classes, so we forget. So can you please repeat the thing once more?
Uh, so to be very honest, I do not also have a very good understanding of Feynman diagrams, based, I mean, advanced topics and it how, matlab, in terms of field theory and so on. Okay, but what it does is that it represents the electronic correlation, or for that matter any particle correlation in a diagrammatic way. So if we try to, let's say, understand from this I mean electron photon interaction process, so so this already tells that you have a plus k electron, so goes from I mean it it is represented by a straight line, and then there is a phonon present with plus k. So all the different kinds of particles are represented by different notation actually. Okay, so here all electrons are represented by straight line, and then these phonons are represented by curly lines. Okay, and this represents that this process, so actually it is a very I mean very compact way of representing so lot of things. One is that the momentum is conserved in the process. So if you so these are the, let's say, initial stage, and this is the final stage, right? So initial stage we had the momentum plus k and minus k 0, and here also you will see that momentum is 0, and there will be some energy of this epsilon k and epsilon plus epsilon of minus k, let's say minus k, and here also the energy will be k plus q, and then energy of minus k plus q. So all of these information are very easily represented by this I mean particular diagram. Now there are so from this diagram people write field theoretical I mean so what is called the Hamiltonian term, interaction terms, that we also will be writing. Okay, but there are other details actually, path integral formalism and so on. So yeah, those details I am also not very familiar with. Yeah. Okay, so any questions? Okay, so the second question was so clearly identify initial. Okay, the second question is clearly identify initial, intermediate, and final state energies, and then show that these processes under certain conditions, we'll see what this condition will be, yield attractive interaction between the electrons. So that was the kind of essence of starting the superconductivity. So uh, why even though two electrons have a repulsive Coulomb interaction, why there is a formation of pairs, right? So that is because of phonon mediated attractive interaction between them. So let me start with, so yeah, so let me start with writing electron phonon interaction. So we cannot fully solve the, I mean, interacting Hamiltonian. Even so, we definitely cannot solve analytically, right? As you have already seen in BCS also. So you had to take a lot of approximation, and then uh, I think mean field was not done fully. So even at the mean field level, we do not solve the interacting picture fully. We just take that mean field limit and then can solve it partially. So the electron phonon Hamiltonian for this case will be okay. So before that, let me write the initial and intermediate and final states energies. So initial state energy will be epsilon of, so for case 1, let's say, yeah, for case 1, epsilon of k plus epsilon of minus k. So this was initial. And then final state energy will be epsilon of uh, k minus q plus epsilon of uh, minus k plus q. Sorry, this is final. And then intermediate will be some state. Intermediate state is, so we have epsilon k plus epsilon minus k plus h bar omega q, let's say. Okay, yeah. So this particular energy is the phonon energy. Okay, yeah. And similarly, we can write for the B state, sorry, second state actually. So so how do we show that these processes under certain condition yield attractive interaction between these electrons? So for this, so what we need to do is that we need to go to this second order perturbation theory. So suppose you have a, I mean, so the initial state, let's say, can be written as I and then ck daggers, c of minus k daggers and 0, right? So 0 is the vacuum state. Now your initial energy will have, if we assume, or we generally, so in epsilon k is of the form of h bar square k square by 2m, right? And for minus k also you will have the same energy. So the total energy for initial state we can think of 2 of epsilon k, let's say. Okay, and then the final state f is like c uh, k minus q. I'm doing for case 1 actually. Dagger c minus k absorb the photon, so sorry, phonon 0. Okay, and the final state energy again you can write, it will just be epsilon of k minus q plus epsilon of minus k plus q. Okay, so these are the initial and final state. Now there is a, I mean, virtual process between these electrons via the phonon, and then there is a attractive potential. So the effective interaction, so between the, so the effective interaction between these two electrons mediated by phonon will be intermediate steps, and then let's say final state, you have a electron phonon Hamiltonian. I'll write what do we mean by that, and then some intermediate step H electron phonon initial step by, so capital E. Okay, so this is what we can get from the second order perturbation theory. So why not first order perturbation? That is because the initial state electrons, so electrons from, let's say, k, starting from this k to minus k. So these are the two initial electrons, and these are the two final electrons, right? It loses this momentum, and then second electron gains the momentum. So this is not happening through first order process, meaning the electrons are not directly interacting with each other and then going to the another final state. Rather, it is happening via the phonon. Okay, so that's why we cannot use the first order, I mean, uh, perturbation results for the effective interaction. Okay, so I'll solve it kind of phenomenologically. Again, so the analytical solution is very difficult, exact solution.
I
Yeah,
have a question.
sure.
So, so from the effective this expression, it is clear that there will be some singularity when AI is equal to I mean, interference, right?
Sorry, your actually voice is not coming clearly.
Uh, there will be singularity at
Mhm.
some point when EI is equal to E
Right,
in
right, right. So those, yeah,
so
that's
what is
true.
the significance of that?
Sorry.
What is the significance of that? Well, I mean physical significance. What does
Physically, actually, those singularity we do not consider. Meaning, if we consider, then these things will blow up, right? So the V effective interaction will blow up. So we do not consider those singularity at least here. And in numerics, of course, we regularize things so that these things do not appear. We actually put an extra iota, eta, and so on. But those singularity, so this will anyway be, I mean, very phenomenological level, I mean, calculation. Just will just determine the proportionality constant. Okay, yeah. But here we do not consider that. Yeah. We'll assume that EI is never equal to EINT. Hello. Okay. Uh, yeah. So the electron phonon Hamiltonian. So again, this is kind of phenomenological. Okay, so it's not a perfectly correct way to derive it. Okay, you must have seen even in the lectures also. It was not fully derived. It was just shown that it will be something proportional to omega square minus omega q square. So that this particular thing needs to be negative. Whenever it is negative, so that V effective is negative. That means it has an attractive potential. That's the only thing I can so we can do analytically just to have an intuitive understanding. Okay, so the electron phonon Hamiltonian we can take of the form, let's say, sum over all the k states, the electronic states, and sum over all the q states, phonon momentum states, and then there is some gq phonon, so the electron phonon coupling strength, let's say, and then we'll have ck plus q dagger, ck, and AQ plus A minus Q dagger. So dagger. Okay. So these C are the creation and annihilation operator, and then A and A dagger are the phonon operators. I mean operators for phonon. And omega Q. So where somewhere where we use the omega Q. Yeah. So omega Q is the phonon frequency. Okay. So this is a kind of the minimal electron phonon coupling you can consider. So initially we had, so in the process electron with momentum plus k, it emitted a phonon of momentum q. So phonon of momentum q and goes to uh, k minus q, right? So the intermediate state for this we can write as uh, like c k minus q. So this state is created finally, creation operator, c minus k, okay, and then AQ. So that intermediate energy will be, as we wrote earlier, intermediate epsilon of k minus q plus epsilon of k. Sorry, somewhere. Yeah, so this is for the, yeah, actually it's correct. But only thing I think epsilon of k minus q, epsilon of minus k actually, plus h bar omega q. Okay, okay, and then for the intermediate energy, I mean, so the process B, sorry, process 1. So this was process 1, let's say, and then process 2. Okay, so before that I need to derive the energy, I mean the difference in energy. So the difference in energy was Ei minus Ei in T. So it will be epsilon of k minus epsilon of k minus q minus omega q. So here h bar is included, okay, always. So then, so for the case 2, let's say, right, yeah. In the second case, so the sorry, minus k emits the photon first, and then the intermediate case will be, we can write similarly, k dagger c minus k minus q dagger. Okay, so I'll come with the easier way to do it actually once this mathematically more part is done. Okay, so then we have delta, sorry, what is that? Delta E for this case as epsilon of k, epsilon of minus k minus q minus omega q h bar. Now this V effective, where so this particular term actually can be written as, so again we're not deriving things, okay, it's analytically not feasible. So this can be written as g of q, g of q, and then 1 plus, so this will be clear from this part actually. You can write as 1 by delta E process 1 plus 1 by delta E 2, okay, and we can approximate that epsilon of k minus q, which means that epsilon, so the energy with momentum k minus q is going to be almost equal, so this is approximate epsilon of k minus vf time q, okay. So you can put also h bar vf, so vf is the characteristics Fermi velocity, so this is vector, and then epsilon of minus k minus q is also going to be epsilon of k vf h bar, sorry, plus h bar vf dot, uh, or rather make it just normal equation q, okay. So that means, so I'm skipping few parts so that we can discuss the other solution actually. vfq minus h bar minus h bar omega q. Omega q is the frequency of the phonon with with momentum q, and then so this was for the one case. So for the second case will be minus vfq minus h bar omega q. So if you plug this in this expression, then V effective will be g of q square, and g of q square is essentially coming from this particular, so you will have this the electron phonon Hamiltonian for the final two intermediate, I mean final intermediate steps, and then intermediate initial states, okay. So from there gq is coming, square is coming, then we'll have 1 by vf, so I'm putting h bar extra q minus omega q h bar plus 1 by minus h bar vf q minus omega q h bar. So this approximately can be written as gq square 2 omega q h bar by H bar, no, no, not omega. Okay. So this effective interaction between electron and phonon. So this interaction energy or the interaction potential can sometimes be negative depending on the phonon frequency, and then of course the electronic information is already there within this Fermi velocity. Okay, and not only the phonon frequency with which I mean the momentum of the phonon. So depending on these three parameters, the V effective can be negative actually. Okay, whenever this is negative, it will have an attractive potential. So the condition is so omega square, or I'm basically we can represent this equation as so H bar omega, sorry, VFQ as H bar omega. Okay, corresponding frequency for the electronic energy, and this is already H bar omega q. So the condition will be omega square minus omega q square less than 0. This is the condition. Okay. So there are, I think, other, I mean, easier. There is actually not easier way. I mean, you know, analytically, it's difficult to derive. Yeah. Okay. So the next question is uh, question 5. Okay. So there are some expressions given. Okay. So that electronic specific heat of a superconducting state or superconductor state is given by this particular expression. Okay. Okay. So to calculate a specific heat, where do I start with, right? So we have a specific heat. We all know that specific heat is T or dq dt. Let's say at let's say constant volume, which can be written as T del S del T at constant volume. So where S is the I mean the entropy of the system. So of the electrons actually, not the system. Okay, so the basic yeah. So from the statistical mechanics, so how do we know to calculate the I mean entropy is that minus kV sum over states and then pi ln pi, right? So pi is the probability of occurring. So this is, let's say, I. So I belongs to states, and then pi is the probability of that state I. Okay. So here, how do we determine the probability? Let's say, right? So the probability will be in this case S is minus kb, and so if so this fk function itself determines the probability of the electrons of having electrons with energy ek. Let's say, so this is actually ek. Okay. So that means we can write it as a, so there can be two state. So one is state with zero. I mean there is no the superconducting states, and then there is superconducting electrons, and then there is n equal to one. That means there is I mean electrons there. So S will be minus, so minus kb, and then sum over all k states, all k. So Fk is already the probability. So Fk ln of Fk. Okay. So this is with the finite. So n equal to one case. So this n is the I mean occupation. So so the state is occupied or not occupied. So these are the only two possible states, right? So then it will be so we can also have unoccupied at k. So that means 1 minus Fk is the probability of state being unoccupied, and then ln of 1 minus fk. So if we want to consider the spin also, so this was I mean the epsilon k or the fk, it do not consider spin, so we can actually include extra two factor here. If you do not include in later part also, it is fine, as long as you remember that we need to count the spin degeneracy factor. Okay, so this is due to spin degeneracy. Okay, so then we can calculate C as T del S del T at a constant volume. So it will be minus, so okay, so it will be minus 2 kBT, and then the derivative on, so this particular part, so it will be sum over K, sorry, into, yeah, sum over K, and then del T of the whole part basically. Okay, so what can we do is that del fk of del t we can write as del fk of del ek. Okay, and then so what do I need to prove? Okay, fine. So del ek by del t. Now why energy will depend on temperature? Because ek was delta square plus chi k square, right? So chi k square was simply the kinetic energy part, kind of, and this delta can depend on the temperature. So superconducting gap parameter. So as you change the temperature, superconductivity itself, I mean, changes. So the gap parameter is also a function of time. Okay, and this is actually when you solve the mean field theory of BCS, then you can incorporate temperature. So delta is a function of time temperature. So the write it as a delta of T square. So that's why this quantity is not equal to 0. Okay, so using this, what we have is that C will be uh, so minus 2 kVT sum over K. So if you solve the first part, let's say, and then ln Fk plus Fk del del T of ln Fk means 1 by Fk del T, right? Plus minus del Fk del T ln of 1 minus Fk plus 1 minus Fk 1 by 1 minus Fk, and then minus del Fk del T. So some cancellation. So this part and this part cancels out. So what we have is minus 2 kVt. Okay. So the del Fk del T part will be common, and then we have this part ln Fk. So ln Fk minus ln of 1 minus Fk. So we can write it as a ln Fk by 1 minus Fk. Okay. So this is the CES. I think, yeah, it's needed to be proved or not. No, we are not yet there. Okay, so now what we need to do, now we need to explicitly take this part. Oh, sorry, just just a minute. Yeah. Okay, so we need to this part and this part individually. So if you actually do the work, so Fk by 1 minus Fk, so this will be 1 by e to the power beta Ek plus 1, and then so this will be, so what will be 1 minus Fk? So 1 minus Fk will be 1 minus 1 plus e to the power beta Ek. So that means 1 plus e to the power beta Ek, e to the power beta Ek, right? So inverse of that, so e to the power beta Ek by e to the power beta Ek. So this part and this part cancels out. So e to the power minus beta Ek. So this ln part, so ln of Fk 1 minus Fk becomes ln of e to the power minus beta Ek. So this means minus beta Ek, this particular part. Okay. And then we need to derive this del f del t. So we had del Fk del t equal to del Fk del Ek, and then del Ek del t. So del Fk, del Ek. So Ek was root over delta of t square plus xi k square. So it will be delta square plus xi k square, and then 2 of delta t del delta t del t, right? So del Fk del Ek del delta of t del t delta t. So you can write back as Ek. Okay. Okay. I think we missed. No, it's fine. Yeah, this up to this point it is fine. Okay, so we can write this part as, for the proof we need to write like that actually. So this part as del Fk del Ek times so this part we can write as so del del t of, let's say, delta square t. So this will give me extra, is that, so there will be extra factor of 2, so we need to take Ek, right? Yeah. Okay, so we have CES equal to, so from here minus 2 kBt minus 2 kBt, and then del F del T, so sum over K, so del F del T is this term 1 by 2 Ek del F del Ek, and then del T of delta square T, and then there was ln term, so ln term is simply minus beta Ek, so minus beta Ek. So the beta term and kBt term cancels out, and this two cancels out, and anything else. So this Ek and this Ek cancels out. So sum over K, okay, so this energy is also not there. So del F del Ek, and then so something missed already, or just a second. Now this expression is correct. Equation 1 is correct. Then this is also correct. So what I needed to prove is the following. So minus 2 by t sum of k ek square beta by 2. Okay. So what are we getting is simply this term is there and then this term is there. So now if we actually do so I needed to prove minus 2 by t sum of k del f del ek square plus beta by 2 d of delta square t by d beta. Okay. So this part needs to be connected to this. Okay. If I go back from here, okay, so there is extra sk square factor. Okay, let me see it. I'll solve this and then update the notes, actually, upload the notes. So we are close to there, but I think this needs to be, I mean, converted to this actually by some more numerics. I mean, more algebra. Okay, so then 6, 8, what is? So the sixth is, so let me jump the page and then so that this needs this. Uh, so 6A is calculate jump in specific heat at t equal to Tc, so that delta C equal to CES minus CEN. So ES is the specific heat due to electrons. So electronic specific, E means electron and S is superconductor and N is normal. Okay, En is normal state. So at T equal to Tc, yeah, and then express your answer in terms of. So the number density or states at Fermi energy and then Boltzmann constant and Tc. Okay. So what we need to find is that CES minus CEN, right? So at TC, so let me figure out what is CES at T equal to TC. So the it the question says you use the result of a question. I mean, question 5. So 2 by T sum over K del Fk del epsilon K, then square plus beta by 2 at T equal to Tc. So this means minus 2 by Tc sum over K. Mm. So at T equal to Tc, this delta term actually vanishes because delta of given the delta T is proportional to, so proportional to 1 minus root of T by Tc. So this term actually vanishes at T goes to Tc. So what we have is del Fk del Ek and then Ek square, right? So Ek square means simply, so Ek square and then CEN. So the normal electronic specific heat that we know actually as a function of temperature. So this is 2 pi square by 3, and then so this is actually for 3D. So N of epsilon F, epsilon F is the Fermi energy, and then KB, so KB square T. So this we can derive actually. Now what we have here now is that, so this term, so CES. So any questions or what? So CES will be minus 2 by TC sum over K. So this will be converted to del xi k square and del xi k, because Ek was xi k square plus delta of t square. Now delta of t at tc goes to 0, so this term vanishes. So Ek is just xi k square. So Ek is just xi k actually. So that means this will be xi k. Okay. Now this particular term, so we had a free factor actually in delta. Just let me check for the questions. Express your answer in terms of n of EF, so number density at Fermi energy, and then okay. So I think the question was actually problematic because okay, so what we got is simply this term. Okay, actually it is correct actually. So what we can do now, I understand. So what we have, so starting from this part, actually what we have is the only, I mean, so we came to this point actually via calculation, right? Now, what we needed to prove is this one. Now, this actually includes both the, I mean, so this is the free electrons, I mean, electrons normal state energy, sorry, normal state specific heat for of the electrons, and then plus the uh, the case for the superconducting. So this part is the superconducting part, okay, and this part is the for the normal electrons. So okay, actually this we can convert to this. So this I'll derive and upload actually. Okay, so uh, from this part you will not get this whole part. Okay, so this was for the normal state and this was for the superconducting state. Okay, yeah, sorry for this. Okay, so now if we come back here, uh, we actually needed to determine something like, so the whole scenario changes, because what we asked to determine is this one. So we have a general CES expression. So CES expression is uh, minus 2 by T sum over K del Fk del Ek, and then E k square plus beta by 2 d delta 2t or del for that matter. So del beta, this one. So this is superconducting part and this is the normal part. So what we need to determine was CES minus CEN. Okay, okay. So this then CES minus CEN would be CES minus CEN would be minus 2 by T sum over K beta by 2 and then delta square T of del beta. Okay, and of course this part is there. So del Fk, so del Ek. Okay, so this is the part. Now we can rewrite this part. So this will be evaluated at T goes to Tc. Someone needs to unmute actually. Sorry, mute. Okay. So we have was it betas? Okay, simply beta. So this we can write is minus 2 kb. So let me write kb and kbt sum over k beta by 2 del delta square t del beta, and then because we have so del fk del ek, right, and t goes to tc. So this part will write as beta, so minus 2 beta square by 2, so 2 cancels out, and then kb we have del delta square t del beta sum over k, and so let me put the minus here, so minus del epsilon of sorry f of k del ek. Ek we can write as xi k in the tc limit because delta of t goes to 0 almost. Okay, and then this turns out, so this part is independent of k, so we can take it outside. So del delta square of t del beta, what we have is sum over k minus del fk del epsilon k, sorry, xi k. Okay, and of course this is evaluated at t tends to tc. So again same thing here, t tends to tc. Okay, okay, and this part, this particular sum over k and minus del f del k is actually give you the number density at Fermi energy. Okay, in the low temperature limit. So we have n epsilon of f. You can think why it will give number density. So how many number of states? Suppose we have a Brillouin zone. Let me write as square, and this particular part in the zero temperature limit. So when t is almost zero, so this is a derivative of Fermi function. So derivative of Fermi function gives you almost delta like peak. Okay, so delta peak. So you have a Fermi energy Fermi function at as a function of energy. Let's say this, so this is the energy. You can write a xi fk. Now as you decrease the temperature, so this almost become very sharp, right? And this is xi equal to mu, let's say chemical potential, where below chemical potential everything is I mean filled. Now I need to take derivative of this, right? So derivative of this with negative sign, it turns out that so this kind of peak will be there. Okay, at the zero temperature limit. So that means, and this is summed over all k. So you have a delta peak at all k and you are summing over this. So that is kind of equivalent to the number density. So the density that is there at the Fermi energy, so at this energy, let's say. Okay. Mu here is actually denoted by, in the question it is denoted as epsilon f. So that's how it is counting the number density at Fermi energy. So we have kb beta square, and this part we need to derive, determine. So del delta square of t, del beta we can write as del t, del delta square of t, del sorry, del t, right? So this we can derive as, so beta is 1 by kbt. So del beta del t will be minus, equal to minus, sorry, plus kbt square. So inverse of that, so minus kbt square, and then our delta expression was, delta of t was, uh, so this was 1.74 delta 0 1 minus root over t by tc. Okay, so we can, the delta square is there, so 1.74 square delta square 1 minus root over t by tc square. So if you determine this, then no, we cannot. Yeah, yeah. So del of delta square, del of t, 1.74 square delta 0. So this is delta 0 square, and 2 1 minus t by tc, then minus 1 by 2 root t. Okay. Okay. So if you plug all of these, so for example, so this root t cancels out, and then this will be simply tc. Okay, so if you include all of these, then what you will get is that, uh, of course, in the t goes to tc limit, t goes to tc limit. So it will be something like, 9.4 10 number density, or the states actually at Fermi energy, and then kb square tc. Okay, so this will be the delta c. Also compute. So the second question was, so you just need to plug this part uh, here. So here actually, so here it will be delta square t, delta t, delta t, delta beta. Okay. Okay, so the question B was, also compute the numerical value of normalized discontinuity where CENT is given as 2 pi square by 3 uh, n at EF, and then kb square t. Okay. Okay. So what you need to find is just, I mean, this is just the numerical calculation actually. We just divide this particular result by this expression C en of t. So 9.4 by n epsilon f kb square tc, and again we need to derive at t equal to tc. So 2 pi square by 3 n of ef kb square tc. Okay, so everything cancels out, and then there will be a factor of I mean 9.4 by into 3 by 2 pi square. So this will be some number. So it will be let me, it is 1.42, yeah, 1.43 actually, almost. Okay, so this was the last question, and then yeah, so there is a question 3 which I didn't solve actually. So question 2 is fully solved in the lecture. Question 3, okay, so I'll actually solve the question. I mean, solve and upload. So question 3. So what question 3 says is that, imagine, I mean, energy gap is given delta, and then superconducting potential for K and K prime are given as minus V0. So and then by solving two particle Schrodinger equation, we need to find this delta. Actually, delta is not given. We need to find the delta expression. Okay. Okay. Now there is definitely one way, second quantization picture. So the way we wrote Hamiltonian. So xi k is some energy, ck dagger, c minus k dagger. Let's say sum over all k state, and of course spin part will also be there, and then sum over k sigma, and there will be another factor L, KL. PKL is the interaction potential, and then of course CK. Uh, so it will be CK dagger, C of minus K dagger, I think, and C of L, C of minus L. I'm writing something. No, I'm not wrote actually. Okay, fine. So I think so VKL, it will be CK and then minus K. So let me see. CK of I need to consider spin actually. So if it is off, then the minus K should be down. So it should form singlet. So suppose I have a Fermi surface, and then at plus K, if I have a off electron, and then minus K, I am creating a down electron, down spin electron, and then I'll have C of minus L. If it is down, then C of L should be up, or the vice versa. Both are possibilities. So that is, so this is one approach. And then what was the second approach I was trying to do is that you solve it fully from a kind of the Schrodinger equation. So meaning you take two electrons, so two electrons at two position, let's say. So R1, R2, somewhere there is a center, and then we'll have the kinetic energy like minus h bar square by 2m gradient of 1 square plus gradient of 2 square. So gradient of 1 and gradient of 2 means particle 1 or electron 1 and electron 2, and then of course plus some potential energy. Sorry, uh, yeah. So this will be the kinetic energy. Of course, it will act on some function psi, and then potential energy will be the potential V, and then we fully solve the Hamiltonian, right? Schrodinger Hamiltonian. So kinetic energy term plus potential energy term. Okay. So this is kind of more of a conventional, I mean, in the real space picture. Okay. Or we also call it first quantization picture, because we do not write things or Hamiltonian like in this picture C dagger and C. Okay. So this was what I'll solve and upload actually. Okay. Okay, so any questions?
Hello.
Hmm.
Could you please share the notes of today's session
Yes,
later?
yes, I'll upload actually. So I'll solve those two problems. One is going from, so this will be the identity actually. So this will just need a little bit of algebra. So this was I think the case, and then we needed to go maybe delta square of t del
I mean,
beta something like.
what are, the today's things what already done in this session. That
Mhm.
also would you like to share?
Sorry, your voice is actually low very.
I
Can
mean,
you? Hmm.
uh, you will solve that question and upload that I understand. But what about the could you please also share this today's note also?
Yeah, yeah, yeah. So this note, this particular note you're talking about, right?
Yeah, yeah, the
Yeah.
whole notes of today's session.
Yeah, yeah. I'll upload the notes actually. So so another one is saying ki, so the video, can you make the week one video available? I think it is already available, right? So you need to go to the or my screen is not shared actually. So in the course page, NPTEL course page, I think you get a Google Sheet link.
No, no, the video is not available there. There is no link.
Okay,
No, video is not there.
okay, okay. So okay, so I'll upload actually. Okay, so this is my mistake. So I'll check and I'll upload. Okay. So it is actually already uploaded, but I think the link is not there. Okay, fine. I'll just update that now, and then this video will be uploaded, I think, by tonight. Yeah. Okay.
Okay, thank you.
Okay. So if you have, I mean, any question in between also, you just write to me at sunitd@itk.ac.in. Yeah, I'm writing in the chat box. Yeah. Okay. Thank you for joining. So I'm uh, ending the meeting.
Thank you.